Okay, yeah, that's a joint work with a number of people. There's Ambrus, who's here, somewhere there. Mike Shulman and Elif are not here. They're in San Diego. I didn't, right? And Shumi is not mentioned in the abstract, but he was involved. He's there. He was involved as well. So I wanted to mention him. So maybe as you have experienced this as well, I mean, there is this very useful types meeting because we started to think, oh, hang on, there is a deadline. We have to submit an abstract. And what do we do? We make some utopical story what we can do in the next year and talk about it. And so we wrote the abstract. And then we told Mike, oh yeah, look, we wrote this abstract. Do you want to join? And he said, yeah, actually, the utopical things you promise in your abstract, I have already formalized in Naria. Thank you very much. Yeah, I mean, whatever. So I'm going to talk about what Mike has done. Mostly, and like some comments by us. Okay. Let me start with something slightly provocative. I know it's very unusual for me. So people always think this is the definition of equality. I think this is one of the major confusions in type theory. It is not. Okay? Stop saying this. It's not the definition of equality. It doesn't define anything. It reflects whatever equality you have, it's reflected in this type. And if you are set sort of 20th century type theoretician, the only equality you have is definitional equality. So this reflects definitional equality. Yeah? But things have moved on. We can actually define equality. So intentional equality is really a bad idea. It actually happens that for inductive types like natural numbers, this equality is the equality we mean, but there are lots of other types. Maybe you haven't heard about them, like function types, just to mention one example. Yeah, so which have a different equality. That's rubbish. And anyway, sorry. Okay. So what is a hot vision? Now, hot with an O, I mean with a capital O, higher observational types theory, which is really an evolution attempt to understand, to conceptually describe this strange beast of homotopy type theory, which also was one historical accident, important one, but so it was. And people always think, oh, to understand homotopy type theory, you have to learn first homotopy theory. Actually, it's the other way around. Learning homotopy type theory gives you a path to understanding homotopy theory. Not that you have to, but if you want to, that's the way to go. What's a type? A type has elements. Okay, colon. A type comes with an equality type. Every type has an equality type. It's part of what a type is. It's not an extra another type. Yeah, it's not a type constructor. A type comes with an equality type. And we can iterate this process, and we end up with this beast which semantically are modeled by omega groupoids. What else can we say? Every function preserves equality, not just every function, every construction, but just specifically function. And this we call apply path. And in hot. And we can coerce between equal types, and that's called transport. Moreover, here's a bit of a vague term. Equality is observational. What do I mean by this? I mean, this is this Leibniz principle. So, for example, functions. You can never observe in types theory a difference between extensionally equal functions. So what are they if not equal? Yeah, I mean, you have to make your mind up. Either you say they're different, and I say, yeah, but there you can't say this. So they're in forever in this limbo of neither this or that. Yeah, I mean, I've seen these people. Function extensionality, a very dangerous principle. Yeah, what else? I mean, what if you don't want function extensionality, then give me quote. Yeah, I mean, this is the alternative. I don't want to have quote, please not. I mean, okay, if you also want to have abstraction, yeah, what about abstraction? Yeah, then don't give me quote. Yeah, give me function extensionality. That's what I want. Okay, good. What's the next slide? So here is what I'm going to talk about. I don't have many slides. Maybe I should slow down a bit. we have developed a theory of parametricity that was already mentioned by Aaron, which is potty name POT. I'm not sure it's a good name. Parametric observational type theory. What does it mean? I'm not sure. So this, yeah, that was a parametricity theory, and our idea was actually to have this as a building block for the theory we really want, which is not a parametricity theory, but a higher observational types theory. And there was also last year's types. We presented a more sort of relational version. I mean, the version in the Popper proceedings has got spans, and then we did this relational. And Mike and Elif, they implemented this. They implemented a sort of experimental system, NARIA, to play around and also expand a bit on this idea. And and I'm going to present some idea of NARIA. You can download it. It changes twice a day or something. I mean, it's still under development. It's a very experimental system. It's the implementation and extension of this theory of parametricity. And what we can do, and this is really cool, so I hope I can explain this, we can define what we mean by fibrant types. So what's missing? We have this theory of parametricity with these famous bridges, which were already mentioned. And what we don't have, we have applied paths, but we don't have transport. So how do we get transport? And there is a nice sort of internal way, even though there's still a problem, which I'm going to mention, to do this, to define the fibrant type, to introduce the types which have transport as a higher co-inductive type, and then to show that all the type formers we want are fibrant. And for one of them, obviously, we are still a bit stuck. So that's work in progress. I mean, come on, this is types, yeah? I hope that's okay. Okay, so here's some NARIA. I thought I start with something simple, something everybody has seen, just to warm you up to NARIA. Yeah, I mean, this is just a definition of natural numbers. Maybe you've seen them before. And the definition of this famous function called addition. Maybe you've seen this also before. Okay, so that's how it looks in NARIA. Not very pretty. It's a bit like, and there's always this maps to symbol. Oh yeah, and it has got this funny rule that constructors end with a dot and destructors start with a dot. So, okay, just some NARIA. By the way, it hasn't got a termination checker. Who needs termination checking? I mean, I've never write non-terminating programs, you know. So come on. So here, okay, so here then these bridges. So I think of bridges as equality, but they're really the sort of logical relation. And the idea of these bridges, bridges for inductive types. This is the right thing. Bridges for inductive types like natural numbers. So we have the same constructors for the bridges. And actually, I didn't want to write this. We have also the same constructor for the bridges of the bridges. So the equalities of equalities have the same constructors. Yeah. So if you have an inductive type, so you have 0. But 0 is also the proof that 0 is equal to 0. And 0 is the proof that bridges of 0 are equal to bridges of 0 up to bridges of 0. So this is the square and then cubes and so on. So we just repeat this, the story. That's actually what Aaron has already mentioned. That's how it looks in syntax. And for example, successor is the same. If you have a successor function from n to n, but successor is also a constructor. If you have a bridge from m to n, you get the bridge of suc of m to suc of n. And indeed, the bridges for a type like natural numbers are exactly equality. So what is the type for which bridges are not equality? No, that's fine. What? The universe. Thank you very much. Bridges for the universe, I will come to them, are not equality. That's where it breaks. You know? But for natural numbers, bridges are exactly equality. And you can prove, for example, addition. I mean, here that m plus 0 is equal to m by just doing this proof, analyzing the number and then returning a bridge. You know? And actually, where does this where do you run in trouble with this approach? When you need transitivity, so for example, when you do commutativity, you need transitivity. However, it's not a problem because you can actually prove transitivity for the bridges. Yeah, that's a bit remark. But okay, so here's something dual. What about co-inductive types? It has also got co-data. The syntax, okay. I mean, I always hope that somebody re-implements Naria with an ACTA syntax, please. So we have a head and a tail, this is definition of streams. And here I do my standard example for streams that from n+1 is the same as mapping successor to the number starting with n. And again, we have that the destructor, the bridges for streams have the same destructors as streams. So intuitively, a stream, a quality of streams or bridge for streams are streams of bridges. Yeah, but that's not a type equality. They just behave the same way. So the same destructors which apply to streams apply also to bridges of streams and bridges of streams and so on. Yeah, so that's very, very simple idea, really. Okay, so bridges in the universe. So here, if you have a bridge in the universe, what can you do with it? Now, yeah, a bridge in the universe gives you a relation. Yeah. So if you have a bridge between two types, then this can be used as a heterogeneous equality. So if you have an element A0 in A0, A1, A1, then I can apply this to the bridge and I get the element in the universe. So every bridge in the universe gives rise to a relation, and using this gel type, we can also go in the other direction. So if you have a relation, you can have a sort of family of types, which is always a singleton, always this relation itself, which so sig stands for sigma, which gives you a bridge. Yeah. So you can go from bridges to relation and from relation to bridges. But what is missing, and we will get back to this, is that if I start with a bridge, turn it into relation, and then turn it back into a bridge, that we would like to be this equal to A2, and this is the one thing which is not supported by this cubical semantics. And I will get back in a second. How much seconds do I have? Oh, 6 minutes, okay. I will get back in the second half to the talk, why we need this. Okay, so now we want to have fibrant types. We have already remarked that we don't have transports, yeah, and this is and that the type of the universe is a type where equality is not, or where the bridge is not equality, because the bridges in the universe are the relations. I mean, and if you have a type with a relation between it, they're not equal. So we want to add something. And here there is this idea of a higher co-inductive type. So you know higher, or maybe some of you know higher inductive types. So higher inductive types are where we add constructors for equalities. So higher co-inductive types is where we define a type by adding destructors for equality. And this is a bit we have to think about it. So isFib is really a predicate on type, so function from type to type. So given a type A, isFib of A says, oh, this type is fibrant. It comes with transports. So if you have two fibrant types and a bridge between two fibrant types, types which are fibrant, then the bridges correspond exactly, give you the transports. And how does this work? We say, okay, if you have isFib, so here's this P, which means this destructor applies to the equality. So if you have two proofs of isFib, which is indexed by a bridge in the universe, you get a function from the first to the second, from the second to the first, and then proves that these functions are heterogeneously equal. Moreover, and this is where the co-induction comes in, the equality itself is also fibrant. So that's what you want. You want to have transports all the way up, yeah, infinity. And now, using this higher co-inductive type, we can define the fibrant universe, which is really what we want, the universe of fibrant types. And if you think about it, the bridges in FIP, so if you have two elements of FIP, then you have a relation between the type and this proof F2, which is exactly fits this is FIP, which means you get the transports, the correctness of the transport. Moreover, that A2 itself is also fibrant and so on. So the equality of the equality, they are all fibrant. And that's what you want. Okay. So now the work we have to do is now to show that all our type constructors are actually well behaved, are fibrant. And it's not very surprising. So for example, you want to show if you have two fibrant types, then the product is also fibrant. And how to construct the transports is not very surprising. They're just the products of the transports. But now to prove the recursive case, you need the fact, which maybe you have noticed this already, that the equality of a type is something of the same kind of type. So equality of products is product of equalities. And you have to, you can prove in area that this is actually an isomorphism. And this isomorphism is up to extensional equality, really. I mean, the equality in the model, to say. So you get this isomorphism, and you can show that isFIP is preserved by this isomorphism, which makes it work. So each time you apply the bridge, it's fibrant because the equality of products, you can apply your co-inductive hypothesis that this is fibrant again. So you get it going. So now, what fibrant types did we show? So it's not difficult. It's not hard to see that 0, 1, 2 are fibrant. For 2, you need that 0 and 1 are fibrant because two elements in Boole are either equal or not equal. That's very equal and easy. For pi types and for sigma types, you use exactly the fact that the equality of pi types is a pi type. The equality of sigma types is a sigma type, which makes your co-induction work. For W types, it's a bit more interesting because the equality of a W type is not a W type, but you need an index W type, and there is a choice. If you do it the right way, then you get that the equality of an index W type is another index W type, and this way you get it going. And same works for M types. Okay, now the core question on which we are stuck in the moment is FIP fibrant. So what we can do, we can actually prove univalence because we can prove a fibrant type is equivalent to bridges, which is nothing else than what you know equivalence. And actually, there are convenient ways to define equivalences, which are very similar to our definition of isFIP, which is basically using a relation which is a function in both directions by using contractibility. And you can prove that you can encode equality in the universe this way. But when you want to prove that encode decode, that this is an isomorphism, then you need exactly this missing equation, namely that Gel of Angel is identity. And this is, as I said, is something which is not justified by the semantics. And the question is, do we have to modify the semantics, or do we find another construction which doesn't rely on this? We don't know. So it seems most likely that we have to revisit the semantics of the parametricity calculus, or do something else. I don't know in the moment. Okay, so my last slide. Assuming that we can overcome this obstacle, so things we need to do is I use this co-inductive type, but we need to have a semantics for higher co-inductive types, and also more an implementation view. While in the moment we use NARIA to experiment with this vibrant universe. That's not how it should look. We really want to, this is just a way to experiment with the semantics. But in the end, we really want to have a native version of higher observational type theory. We also haven't done higher inductive types, which I mean, there's an interesting twist there, because if you just do higher inductive type naively, they are not vibrant. So you have to have a vibrant replacement, which means you have to add a constructor for vibrancy. But this is actually a similar story as for cubical actor. And interestingly enough, Mike has already played around using this parametricity calculus. You can define semi-simplicial and semi-cubical types. Semi-cubical because we have this binary parametricity. Maybe we can also unary parametricity. We get simplicial types or some variant of simplicial types. But anyway, so having semi-cubical types, if they are vibrant, would solve a big open problem in hot, because we would be able to do hot and hot, or HOTT and HOTT. And one thing which I forgot to mention, you can also have this semi-vibrancy, where the vibrancy is only in one direction. And I think that gives you a good handle to directed type theory. So because then univalence just says that the Hom type of the universe is functions. Okay, thank you.